Hello everyone and welcome to We Meet at Digital Days. My name is Lisa Richter and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Transformer Design for EMC Practical Construction Technique. Our speaker is Tomas O'Brien. He will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. And you will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes left for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the presentation, you'll be asked to participate in our feedback survey. We would be pleased if you take the time to fill out a survey and help us to improve our event. You'll receive the link to the presentation in the next few days, and the recording will be available at our website shortly. So now I will hand over to our speaker, Tomas, and I wish you an exciting presentation.
Hello, everyone. Thank you very much for joining me, and thanks, Lisa, for the nice introduction. So today, as Lisa mentioned, we're going to talk a little bit about transformer design for EMC compatibility, electromagnetic compatibility, and some practical construction techniques to go along with that. So magnetic components are at the heart of every power supply. And when we also need to isolate the secondary side from the primary, we need to use a transformer. And today we will look at how the transformer impacts on EMC and what we should avoid when we're designing our transformers so that our EMC is minimized. Then some good practices we can take in designing our transformer. And then also, if that's not enough, what extra additional measures we can take within the transformer design to reduce the impact it has on the EMI spectrum. So firstly, today we're going to look at a model for a transformer. This is very important because the transformer is not an ideal component. If it were, the ideal scenario is we just have inductance as a parameter on the primary winding here and also on the secondary. And we have our turns ratio of primary to secondary. But yeah, unfortunately, the world we live in is far from ideal. And I think everyone knows that, not just engineers. And as engineers, we need to take precautions, and we need to understand what the parasitic elements are and then the impact that they have on our circuit and in this particular case on the EMI. So what are these parasitic elements? Well, we have resistance of the windings. So the transformer is made up of several turns of wire, copper wire usually, wound around a coil. These obviously have some resistance, and the longer the copper and the thinner the diameter, then the higher the resistance is. So we have this on the primary and the secondary. Then we have another inductance which is in series with the transformer. So this is an unwanted inductance, and it's caused by imperfect coupling between the primary here and the secondary. So all transformers will have some non-perfect coupling, and that coupling is appropriately then called the leakage inductance. So the basically inductance that doesn't couple from the primary to secondary. And another element or elements that can cause some problems for EMC and in general in the circuit is capacitance, intra-winding capacitance or distributed capacitance. And this is actually the capacitance between each turn of the winding on the winding itself. So the primary is made up of several layers of wire. Each wire will sit beside the adjacent wire. Then often we have more than one layer of wire making up the primary, and so we have effectively parallel plate capacitor between the layers, and these will have some capacitance. The capacitance is small, but at the same time, when we have high switching speeds, it starts to cause some issues. So we have this intra-winding capacitance on the primary and again on the secondary side. And then what's very important is this other capacitance is called inter-winding capacitance. So this is the primary secondary winding capacitance. So we have our layers of primary wound, then we have some sort of barrier, usually tape, and then we have our secondary wound, usually on top or sometimes below or sometimes even sandwiched in the middle. And so there's a boundary in there, and that boundary, that there is a capacitance between, say, then the primary and the secondary. And that primary secondary capacitance, this interwinding capacitance, is the main path then for the common mode noise to flow from primary to secondary, and that is a problem because that current has to find its way back to the source, and so it usually finds its way back from the secondary, so it's maybe capacitively coupled with some earth, and then it goes back to the source, and then that will show up then as peaks in the conducted emissions spectrum. So this is very important, interwinding capacitance. So the transformer is of course a passive component and it doesn't generate any noise itself. However, in a switch mode power supply, the transformer's primary driving winding, so this winding here, is always connected to a switch, typically a MOSFET. So here, so we'll always have a high frequency wave going up and down here basically on the primary side, and then we have a capacitance to the secondary, and so we have a path then for noise currents to flow into the secondary winding and then back to the source on the primary. And when that current does flow, then it will show up then as peaks in the conducted emissions from 150 to 30 megahertz is where we measure the conducted emissions. But that's only half the story. We also have lots of turns of wire wrapped in a coil around a core, and we have this high frequency switching signal in this coil, and that can act and will act like an antenna. So this antenna produces H field, which is basically related to the current, and then an E field, which is related to the voltage. And those two fields then can radiate outwards from the transformer, and indeed from the other circuitry on the board as well. And the H fields can couple into all the external circuitry, so the PCB traces, other components, the cables, and then external circuitry. And then the coupling into those then will when it couples into those, then they can act as antennas as well and redistribute the radiated noise further. And so when we do our measurements in a chamber or in an open field above 30 megahertz, we can see these peaks in the radiated emission spectrum. Typically over 30 megahertz up to 1 gigahertz or even beyond if the switching frequency is high enough. So what does a typical conducted emission plot look like? So here we can see a typical switching signal on this one is a flyback transformer design. So we have our voltage signal here on the MOSFET. When we turn on the MOSFET, so basically the voltage across the MOSFET is 0. Then we have our full voltage. We have a V-bus voltage on the top side of the transformer, and then we have 0 on the secondary side. So we have large voltage across the primary winding. And that will cause current to rise in the transformer winding. So current rises from 0 in this case up to some peak, and then we turn off the switch, and then we have a voltage swing back across the MOSFET, and we have some ringing here. This ringing is actually a factor of the leakage inductance in the transformer. So that leakage inductance is very important for one, I guess, efficiency. So that the higher that leakage is, the lower that efficiency is of the power supply. Often we need to clamp that this voltage, because if it goes too high, then we can damage the MOSFET if it goes above the voltage rating of the MOSFET. So we often employ a snubber circuit on the primary to clamp that or to dampen it. Also, with this ringing of a high frequency, it can cause radiated emissions problems. So leakage is a bit of a killer there. Then we can also see we have, as we turn on the MOSFET, we have a current spike here. And if we were to zoom in on that, we'll see also ringing on that signal. And even on turn off, we get some ringing here. And all these high frequency ringing noises, voltage and current, they will cause some EMI noise. And of course, the fundamental here itself will cause a noise to be generated. And this fundamental switching frequency, we can see in the conducted emissions plot here. So actually, this is switching at 116 kilohertz. And then if we look at the frequency spectrum, or the plots from the EMC analyzer in the conducted emissions lab, we can see then at every multiple of the fundamentals. So here we can see 230 kilohertz, which is double the fundamental. We have a peak. Then we go a little bit further. We have another peak at 3 times the switching frequency, and so on, all the way up here. And then we can kind of see the peaks all the way up to about 5 megahertz. Then the plot gets a little bit, less obvious where the peaks are. They're still there, but as we go up in a logarithmic scale, it gets harder and harder to see them. But then later on, we start to see peaks again, but these are larger peaks, and these are caused by resonances within the circuit. So we have like a low impedance somewhere in the circuit, and it's causing this peak to appear here. So we have to make sure then that we have something in place, either filters to keep this down, or ideally to reduce it at the source. And that's what we want to try to do with our transformer, reduce it at the source. So that was the radiated. Then I explained a little bit about those high frequency turn on and turn off cycles. They'll always have some sort of spikes and ringing due to the parasitic capacitances and parasitic inductances. And that high frequency ringing then will show up then on your radiated plot. So radiated plot starts at 30 megahertz and goes all the way up to 1 gigahertz in this case. And we can see there's some always some peaks and troughs in there. Anywhere where we have peaks, actually, you can usually analyze the circuit at those turn on and turn off, and we can often find the actual frequencies of the noise there. If we look at either the current or the voltage, we can correlate those to somewhere in the circuit where there is a high frequency ringing on the turn off and turn on. Yes, so we can sometimes dissipate these high frequency noises by introducing some impedances in the circuit. So some ferrites will dampen the circuit, dampen the noise, or even sometimes a resistor can do the job. Of course, there will be some losses there, but small loss in efficiency is definitely a small price to pay for a pass in the EMC chamber. I think it's one of every engineer's worst nightmare is failing EMC in the chamber, because yeah, chambers are a little bit expensive to do your tests, and also it's not so easy maybe to find the source, and maybe a little bit too late to when your product is just about to go to market and you're doing your EMC tests. It's yeah, sometimes puts a bit of pressure on the project, so something we would like to avoid. So first of all, we'll look at what we should try to avoid in the transformer. So these are some pictures here of transformers with flying leads. So what are flying leads? Flying leads are, well, basically what are not flying leads. The standard way we wind the wire, we connect it to some pins here and terminate the wires to the pins, wrap around and then dip the pins in solder to connect them to the pins, and then these are connected to the PCB. So this here on this transformer would be the primary side, but on the secondary side, we've wound, usually we'll wind with some safety wire, insulated wire. Triple insulated wire would be an example, or FIW is another example. This is special safety wire, which has a high voltage rating and is approved for safety. So we don't actually need to meet any distance between the primary and this wire itself. We just need to, yeah, we need to meet the distance between the primary and, yeah, where we remove the insulation. So if we don't connect these leads to the pins themselves on the secondary side, where we actually leave them flying, then we can achieve very high creepage and clearance distances. But that may seem like a great thing. We get very high creepage and clearance distances and a small footprint on the PCB, but there's a drawback. These leads are typically very long. There's generally input into PCB, and there's very little control over how the leads will lie in the PCB, these long leads, and so they can go anywhere. So they will make, yeah, basically great antennas. And great antennas are something we want to avoid for EMC. So flying leads really need to be avoided where possible. Yeah, another thing we can avoid or should avoid is this type of core. So this is an EI shaped core. Maybe fairly obvious why it's called EI. This bit here looks like an E. This bit here looks like an I. And in some transformers, specifically flybacks and in all inductors, we need an air gap. So the air gap basically is the main storage part for the energy that we want to transfer on the off time. So on the on time, the energy builds up in the core, but is stored in an air gap. And so we need to create an air gap in all inductors, and definitely as well in a flyback, which is not technically a transformer, it's a coupled inductor because of this air gap, but flyback is a very popular topology, and so we need an air gap. And the air gap, because it stores lots of energy, it holds a very strong H field, and this H field in the air gap, it will, because of the air gap, the permeability is a lot lower, so the H field will radiate around these air gap locations. So when we want to create an air gap in a core like this, we add maybe some mylar tape or some paper in here to create a fixed distance between this core and that core. Yeah, but in this case, we get actually 3 separate air gaps. We get one here, we get one here, and one here. Yeah, and not only are we have 3 air gaps, but we also have the air gaps very close to the external sides of the transformer. So it's not like in the center, it's on the side. And so any components that are placed around these air gaps will absorb some of this H field, and basically there will be noise generated in those areas. And we have no shielding of the windings or anything like that. They're very exposed there. So this type of core may be cheap and easy to use and readily available, but it's not a very good solution for EMC. Now, let's look at maybe some things we can do to reduce the EMI impact of our transformer. As I mentioned before, we often need an air gaps in inductors and for sure in flybacks. But when we do need an air gap, then the best way to do it is to just do it in the center tab. So basically we grind the distance we need on one of these legs, and so we have an air gap here and no air gap on the external legs. Now in reality there is a very small air gap on those parts once you cut the core at all. You know, on any core, any cores where they're separated, there is technically a small air gap in there, but it's very, very small, and the leakage flux will be very, very small around the outside legs. But we'll have a large leakage around the inside leg, but that is at the geometric center of the transformer, and so furthest away from all the external components here. Also, there'll be some shielding by the windings which wrap around this, and so this H field will not emanate into the surrounding circuitry and near so much as with the air gaps on the EI type core, which were say here and here. So this is a much better practice for EMC to have a center leg air gap in here. And no air gaps here, and just put the air gap on the center leg. Yeah, another thing to bear in mind, and maybe a general principle, is to make our transformers basically as small as we can. Why is small better? Well, the smaller we go, the less capacitance we have. I mean, we have smaller plate capacitances between the layers of windings because we have smaller area on the core. We have shorter, smaller leads, so smaller antennas on the leads themselves and in the windings, smaller air gap internally, and we have less leakage inductance because basically it's smaller, and there is better coupling between the primaries and the secondary just based on the geometric size of the thing. So we end up with less parasitics, which will ultimately mean less conducted and less radiated noise. And now let's look specifically at one of the parasitics, and here we're looking at the inter-winding capacitance. So what is a capacitor? Or parallel plate capacitor is made up of two plates, one on top of the other, with some dielectric material between them at some distance. And the formula for capacitance is C equals epsilon R times epsilon naught A divided by D. So the epsilon R here is the relative permittivity of the dielectric material here. The epsilon 0 is the dielectric constant of a vacuum, so that's always constant. So we have just this one we can play with. We have the area of the plates we can play with, so we can make this area bigger or smaller. This is the area that's overlapping basically, which is the area we're concerned with. And we have the distance between the two plates, and that's something we can look at as well. So on a typical transformer, we'll have, say, a primary winding here. and often it's made up of more than one layer. So we have one layer here, then another layer. Then we have some tape or some barrier between the secondary. So what does this look like? It looks very much like this parallel plate capacitor. We have this winding, which is one plate, and we have the secondary winding, which is the other plate, and then we have some tape or maybe some air as well in between them, which is the dielectric in between them. How can we reduce this capacitance then? Well, we can reduce the area. So how would we do that? Well, we could use a narrower bobbin, a narrower winding window here. So if we were to move this wall of the bobbin in this way, we would reduce this area of overlap. Of course, we have less room in there, so it's not so easy to do. Then we can use a multi-section bobbin. What does that mean? Well, it means if we wanted to reduce that area, we could have a bobbin with a wall in the middle here, say, and then we could wind our primary just in this section and our secondary in this section. And then we would have much less area then between the primary and the secondary. We just, the area would be just this boundary here, which is far less than, say, the wide area we have here. Then another thing we can do is increase the distance to reduce the capacitance. How do we do that? Well, we can simply use more tape or use thicker tape here. So we increase the distance between this winding and that one. We can use thicker insulation on the wires themselves. So we see that we have the copper here and we have this red outline, which is the insulation on the wires. So if that insulation gets thicker, then we increase this distance between the copper plates of this parallel plate capacitor. But there's a note of caution here. All these measures will increase the leakage, and the leakage is a killer for efficiency in the transformer, so it comes at a price. One maybe nice way to reduce the capacitance is to reduce this relative dielectric permittivity. And how can we reduce that? Well, we can use very low dielectric varnishes or potting compounds. If we were to varnish the whole transformer or pot the whole transformer, we could pick compounds that have a relative low dielectric constant, or even better, use none. And air has a dielectric constant close to 1 or just over that of a vacuum. And so that's the lowest we can basically get outside a vacuum. And so if we don't use any dielectric or don't use any potting material or varnish, then we have the best case for our capacitance. And the beauty of that is it does not increase the leakage as well. So it's a nice way to reduce that capacitance. So then there are also good approaches we can take in how we wind our transformer, which significantly help to reduce the EMI. The drain of the switching node of winding should definitely not be adjacent to this primary secondary border. So on a typical power supply, again, we have this our primary winding connected to a switch. And this node here, this is the real noisy point of the power supply, and this is always the highest source of EMI generation. So we need to be very careful when we're doing our layout, and also in how we connect all the components and on the board. But in the transformer, we can take some care as well to reduce the EMC impact of this node. So typically when we're winding the transformer, the best practice is to keep this noisy node as far away from this primary secondary boundary as possible. So this won't really have any effect on the capacitance itself. We saw the capacitance was basically a function of the geometry of the thing, but the current that flows, the noise current that flows from the primary to secondary, is a function of not only the capacitance, but also the rate of change of voltage. So the dVdt of the voltage. So we can see on this point here, yeah, we have a very high dVdt. So we have this, yeah, on switching time and the high voltage change. But on this point here, so this is our VBus, yeah, we have a almost constant voltage on VBus. So the dVdt on this point is very, very low. So it totally makes sense where we have more than one layer of winding on the primary to keep this high voltage node away from this boundary. And so we have a lower dVdt on this layer. So here it's almost zero. And as we go along the layer, it slowly increases and increases and increases all the way until we get to the switch node itself, which is the highest. So yeah, makes sense to keep this node as far away from the boundary as possible. So in a typical winding, we would start with the switch node as the very first winding closest to the center of the transformer as well, which is a good thing. And then wind subsequent layers on top. Then also the secondary winding is usually lower voltage, a little bit quieter. We might have an auxiliary winding as well, and these can also act a little bit as a shield to the noisy winding from the primary. So helps our EMI to have those the lower voltage ones on the outside and the higher voltage on the inside. So say, yeah, we've taken all those measures and still we're failing in the EMC chamber. Is there anything else we can do with the transformer? Fortunately, yes, there are a few other things we can do. One is to have a primary secondary shield. So this is basically a thin, very thin layer of copper foil wound and wrapped around between the primary secondary border. This shield then is connected to some quiet node in the power supply, so typically maybe the local ground or VBus. And this shield, the ends need to be isolated from each other, because if they're not, then this will constitute a short circuit, and that's not a good idea. Then basically the whole transformer is a short circuit, and will get very, very hot. So you need to isolate the ends. Also, it's a very good idea to keep this copper as thin as possible, so to reduce eddy current losses that can be generated in there, and we can get very nice results. So this shield will actually deflect some of this noise currents that I just talked about on the previous slide, and bring them back locally to the ground. So instead of going into the secondary, they will get deflected back to the primary, and so they don't go back to earth outside the power supply. So they're contained locally, and that will reduce the common mode noise basically that's generated from the power supply. And here we can see a demonstration of the power supply I worked on. We have this is the high orange line here is the conducted plot before the copper shield. Then with the copper shield, we can see we have here maybe a 5 to 10 dB microvolts reduction, all the way up to maybe 12 megahertz there, which is a very, very nice improvement. And that's the peak. When we do the average, then plot, we should expect much lower, and that was a good pass. Yeah, that shield is one way. It's a little bit expensive to implement. It's kind of a very manual process. And is there a cheaper way to do something like that and maybe get similar results? And the answer is yes again. So one way is to do a winding shield. So this would be a very thin wire wound, very very tightly across. So all the layers should be, or all the windings should be close to each other, and that's why we use basically lots and lots of turns of a very thin wire. The thin wire again reduces eddy current losses, and that can be wound between the primary and secondary all the way along the bobbin. The more copper we have in there, the better. So we want to fill as much area as possible to have a good shield as possible. And then the one end is connected to the quiet node again, maybe local ground or VBus, and then the other end is left floating and then can be buried in here between some tape so it doesn't cause any dielectric problems. That is a good way to do it and is for sure reduction in cost, but this burying of the manual lead or of the floating end is not ideal. And is there a way we can maybe automate the whole of this process? And again, the answer is yes. So we can do the exact same thing. We wind all the way across and then we just terminate the other end to an unused pin on the bobbin. If we have one. We can do this then wind all the way across and terminate to the other side if safety allows, or we can wind all the way across and we can drag this wire back to the primary and terminate to an unused pin on the primary, and that then can be fully automated, which is a very cheap and nice way to do a layer. Maybe the results are not quite as good because there's still some gaps in here from the winding, but we can get a big saving on cost and also quite good results. Another thing we can do as an after add-on is a thing called a flux band. So this flux band is a thin layer of copper again wrapped around the outside of the whole transformer. So this, because it's wrapped around the outside of the core, it doesn't constitute a turn, and so this actually flux band is basically soldered together to form a loop, and then this will be typically connected to a quiet node as well. It can be left floating and still have some good results. This would shield radiated noise. It basically conducts any leakage flux that flows outside the transformer and contains it here. So again, this is very important that this is as thin as possible because it will heat up. There will be some currents generated by the H field in this, and the thinner we can make this, the better for losses. So some disadvantages of this is it only shields radiated noise. It's a little bit more expensive than the internal wire wound shield, and it can increase the transformer temperature a little bit, so we need to just watch that. Another thing that can be quite successful is core grounding. So this is one method to do this is basically we get a little strip of copper, we attach it with an adhesive that's conductive. So the adhesive contains some conductive elements. We glue that on then to the bare core, and then we'll attach a lead to that and attach that to, again, a quiet point in the circuit, a grounder, maybe VBus, some voltage that's stable, and that grounds the core and so stops the core from, which is normally floating, and that can have very good results for both conducted and radiated emissions, and can be added as well after the transformer has designed. So if we have a fail in the EMC house, this one can be implemented afterwards. Again, it's not the cheapest thing to do, and it's quite a manual process again. So if we don't need it, we wouldn't use it. Some other things that can be done for SMG components, we typically need some flat surface on the top, and the flat surface usually is created by some sort of a cap we place on the top of the core. If this is a metal cap, then it can provide some shielding, and now that's kind of reflects some of the currents back and can be a little bit of shielding. But if we actually get some of those caps with solder tabs, then we can actually ground those. Now these are not so readily available and a little bit expensive, so again, they wouldn't really be used unless we had to use them, but can work in the case where EMC is a problem. Then there are some cores which are called closed cores, and we can see here 5 of the 6 surfaces here are actually enclosed in the core, and that this will absorb some and reflect some of the EM field from the windings, and can shield a lot of the radiation that will come from the windings. This one, the EP style core, is no cost other because if we're using that core anyway, so it's a built-in solution and can be very good. And then even to improve that, we can add a clip with some ground tabs as well and solder that to the local ground as well to make it even better. So there's some of the techniques that can be used. Thanks very much for your attention today. I hope now we can open the floor to some questions, and yeah, thanks very much. I hope you found the presentation interesting and learned something.
Thank you very much for the interesting presentation. Yes, like you already said, we will now take our attention to your questions. Just have a look what comes in. I think there's the first one. Have toroidal cores a lower parasitic capacitance if the primary and the secondary windings are wound on opposite sides of the core?
Yeah, for sure. Yeah, I mean, that's a very good way to reduce the parasitic capacitance. So when a toroid is basically like a donut shape, and there are lots of ways to wind a toroid. Often the primary and secondary can be wound at the same time, so bifilar. But the disadvantage of that is the windings are basically on top of each other, very close to each other, and so the capacitance between them is very, very high. To reduce the capacitance and also increase the dielectric between the two of them, sometimes it makes more sense if you have space to wind the primary and the secondary on opposite sides of the core. Yeah, this is often done for gate drives as well, where capacitance between primary and secondary is critical. They'll wind primary on one side of the core and then the secondary on the secondary side or on the other side of the core. So the wires basically don't touch. And if they don't touch and they're far away from each other, then the capacitance is drastically reduced. So yeah, the answer is yes, a good idea if you want to reduce capacitances to separate the windings on the toroid.
Okay, great. And there's a question to page 14. Why there has to be attached a wire to a shielding winding on page 14 and then led to the center?
On page 14. So let me just jump back to that. Yeah, so yeah, for a shield, the shield, we always have to have one end floating, because if we don't, the wire winding will be a short circuit. So we only attach one side to the ground point or the quiet point. Then the other side needs to be left floating. So in this case, we leave it floating by we just simply bury the end of the wire here. Yeah, then the other option was to terminate to a pin, but that pin cannot be connected to anywhere in the circuit because otherwise it won't be floating. So that needs to be left floating as well. So this is just simply if we have no pins to attach it to, we would leave it buried in the center there of the core. So it doesn't need to be in the center either, but this is just a way to this will be magnet wire. There'll be insulation here. At the end where we cut it, this is bare copper. So we want to keep the bare copper away from any other wire so we prevent any dielectric problems. And so we need to cover this with some tape. So yeah, this is maybe an exaggeration. We might just bury it here, but we just need to keep it away from the edges here so it's away from the secondary. So basically that's the reason why that wire is left floating like that.
Okay, so cost of the time, I think we'll just have time for one more question. The others will be answered via mail afterwards. So the last one, why does the flux band not act as shorted winding, which reduces the transferred energy?
Why does the flux band not act as a shorted winding? Yeah, that's a good question. So the flux band, so when the case of an internal shield, so the internal shield is where it's like a standard winding. There's a wire wraps around the inner leg of the core, but on the flux band, we'll see it's wound around the outside of the core. So yeah, the flux in the core, so we have, this is a E-type core. Flux goes from, say, the center out around here on both sides and back in and around on this side, and it also goes around on this side and back in and around on the outside. So to have a winding in the transformer, we need to, in this case, we need to have wires wrapped around the center leg. In this case, we don't wrap around the center leg, we wrap entirely around the outside surface. So it's not a winding, it's a flux band, so it only picks up stray flux that's flowing outside of the transformer. So this is why we can short this and it doesn't constitute a winding. If it was gone inside here with the wires, then it's a totally different story. We short that and then we basically have a shorted transformer and we only have a small leakage inductance of the transformer. So it cannot be shorted if it's internal on the transformer, but it can when it's external to the transformer because it doesn't wrap around the internal leg of the core. So I hope that answers that question.
I think so. Otherwise, we can just answer via email afterwards.
True.
So thank you very much, Tomas, for your presentation. I think now we have to stop at this part to have time for the next one, which starts at 10 with the topic. 1 second, I will show my screen. So design considerations for flyback transformer. Yes, the presentation starts at 10. Hopefully see you there, and so enjoy our digital days and have a good day.
Thanks.
So
bye.